Previously, we saw that given two continuous functions, we could combine them in different ways to obtain new continuous functions. For example, we can add continuous functions to obtain continuous functions, or multiply, or even to consider the quotient of continuous functions and obtain, again, continuous function. In the case of the quotient, of course, we have to be careful to make sure that we never divide by 0. But other than that, we know that we can add, multiply, and divide continuous functions to obtain a continuous function. In this video, we're going to see another way of combining continuous functions that will also give us a continuous function, and that is using composition. So let's get started. Here, this theorem tells me the following, that if I have two functions, f and g, and I know that the limit as x approaches c of g of x is equal to L, and I know that f is continuous at L, then the limit as x approaches c of f of g of x is equal to f of the limit as x approaches c of g of x. That is what pulling the limit inside of the function f. So let's see how we can prove this. Well, since we know that the limit as x approaches c of g of x is equal to L, then what we really want to prove is that the limit as x approaches c of f of g of x is equal to f of L. So that's what I'm going to try to do. We need to first fix an arbitrary positive number, epsilon, as usual. And now we'll need to find a delta such that if the absolute value of x minus c is strictly greater than 0 and is less than delta, then the distance between f of g of x and f of L is less than epsilon. And let's see what do we know and see how we can combine the things we know in a nice way. You see, we know that f is continuous at L, and that tells me then that there exists a delta 1 positive such that for every y, if I know that the distance between y and L is less than delta 1, then the distance between f of y and f of L is less than epsilon. And remember, here we're using continuity, so we can allow y to be equals L. That's something that is very important to keep in mind in this proof. Okay, but now we also know that the limit as x approaches c of g of x is equal to L. So how can we write that down? Well, for that delta 1 that we obtained previously using the fact that f was continuous at L, we're going to find a delta such that if the distance between x and c is less than delta, but x is not equal to c, then we know that the distance between g of x and L is less than delta 1. Oh, but you see now what we're going to do is snake our way through. We're going to concatenate these statements because we see that, well, g of x, I can just call it y, and then things should work. Let's see. If I combine what I said before with this, and we set y equals g of x, we have the following. If I know that the distance between x and c is less than delta and greater than 0, then I know that the distance between g of x and L is less than delta 1. But that implies that the distance between f of g of x and f of L is less than epsilon. And that is exactly what we wanted to prove. Okay, so far as you can see, I didn't ask my function g to be continuous. I only asked for it to have a limit, and we obtained this result. So we're allowed to pull the limit inside this function f when f is continuous. But now we're going to use this theorem to prove that the composition of continuous functions is also continuous. You see, if I have that g is continuous at c and f is continuous at g of c, then the composition is continuous at c. So this f, like circle g, that means composition, and that is f of g of x. Okay, so now that we have these, what can we do? Well, using the previous theorem, we know that the limit as x approaches c of f of g of x is equal to f of the limit as x approaches c of g of x. But I know that my function g is also continuous, so the limit as x approaches c of g of x is just g of c. And that is exactly what we wanted to prove, that the limit as x approaches c of f of g of x is indeed f g of c. And that completes the proof.